Welcome to this new session. Class we discuss some examples of isomorphism, and then we have to prove some basic properties of a isomorphism. In the last class, if you remember, we have to show that the two group we have to taking as a Z4 under addition, and we take a G is the fourth root of unity is equal to 1 minus 1 I and minus I, and then we show that these two groups are isomorphic to each other. This means they are we have to show that there is a bijective property in this form. Phi of 0 is equal to you have a 1, and now phi of 1 is equal to you have a I, and phi of 2 is equal to you have a minus 1, and phi of 3 is equal to you have a minus I. Now, if you see by the this 1 and 3 are inverse to each other, and then you see I and minus I is also the inverse of each other. 2 is a inverse of itself, and then minus 1 also the inverse of itself. That means this preserving the inverse also an identity. This means clearly this is the identity. So, this group we have to last class we discussed this group, and then we show that these two groups are isomorphic. Now, we take two groups. One is a set of real number under addition, and another is a set of real number, a non-zero real number under multiplication. And then we try to show that we cannot find any bijective from R to R star, and that means if it is not a bijective function, we can define in such a way, and this is not an isomorphic. So, we try to show that this means R and is does not isomorphic to non-zero. This is under addition, and this is group is under multiplication of a binary operation. Okay. So, suppose suppose there exists a 1 1 and on to function from R to R, and then with the property of this. This is homomorphism condition is there. And now, one thing is very clear, because you see if R is equal to is a group under addition, then the identity element of this is equal to 0, and this is a group of a G1, we can say that then identity of this element is clearly is equal to 1, because this is a group under addition and this group is under multiplication. So, we can simply say that R under addition is additive identity is equal to 0, and R under R star under multiplication, the identity is multiplicative identity is equal to 1. So, we have tried to show that this is not a isomorphic. So, we suppose that means there does not exist some map which is not a, or the maps which is not a 1 1 and on to, or which is not a bijective and homomorphism. So, we just suppose there exists a 1 1 on to homomorphism, 1 1 on to homomorphism means from phi R to R star with the property because this is under addition, phi of x plus y is the same as a phi of x into phi y. So, one thing is very clear, if this whatever map we have to define, this is phi of 0 is always going to 1. So, by the identity we have to know that this is equal to phi of E is always equal to E1. So, this means phi of 0 of R is the same as the identity of this. This means the identity of this 0 into this form. So, one thing is very clear, we can say that if x is the element of R and such that f of phi of x is equal to minus 1. So, if phi of x is equal to minus 1, then you get a phi of 2x can be a phi of x then is equal to 1. So, in this case, because the theorem is saying that identity of R positive is a unique element. This is okay. This is a unique element of R corresponding to the identity of this. This means if we have a 1 1 onto 1 1 correspondings are there, then identity element is a unique for this. This means 1 we have to assuming that 0 is equal to 1, and then also we have to show that this is the same as a phi of 2x, and by the 1 1ness we can say that 2x is equal to 0. This implies that x is equal to 0. So, this means we can say that phi of 0 is also equal to minus 1. So, this means clearly if phi of 0 is also equal to minus 1, that is not possible, because phi of 0 is always going to the 0 with the properties there. So, there is consecutivity phi of 0 is equal to 1 and phi of 0 is equal to minus 1, and that means contradicting the function phi is 1 1. And that means we can say that this argument shows that R cannot isomorphic to or no function satisfy the definition can be exist in this form. So, because phi of 0 is always maps to 1, and then we can say phi of 0 is also mapping to -1, that means there does not exist any function which is saying that which is a 1 1. So, this contradicting the 1 1ness of this function, this means clearly. So, we can simply say that R positive cannot be isomorphic to R star under multiplication. So, and then this is not satisfied our definition for isomorphism. So, whatever definition we have isomorphism, this does not satisfy our definition of this thing. Okay. So, now we have to try to change this little bit. In place of a R non-zero real number, I take a positive real number and then try to show that under multiplication they are isomorphic. Again, these two groups is isomorphic, that means there exists a bijective, and that again you have a identity of this group E is equal to 0, and identity of this group you have a again is equal to 1. So, whatever isomorphism we have to define is a one bijective function, homomorphism, bijective homomorphism, with where this one condition is very clear, phi of 0 is equal to you have a one identity element. Okay. So, we prove this, we must produce a 1-1 1-to-1 homomorphism, this onto R positive. So, suppose we take a function y is equal to phi of x is equal to e ki power x. So, phi of e ki power x where x exponential function, and then you can clearly say that this is clearly is a homomorphism, and then we can say that phi of x plus y can be written as a e ki power x plus y, and then exponential of e ki power x phi is the same as e ki power x e ki power y, and e ki power x is equal to phi x and this. So, this means whatever function, and this is also clearly is a well defined function is there, this is a satisfy this condition in this one. So, this means clearly this show that is a phi is a homomorphism, and then we have to try to show that this is phi is also is a 1-1 and also onto-ness is there. So, is a bijective, then this phi is a 1-1 means phi of x is equal to, we have to show that phi of x is equal to phi of y, that is this is clearly this e ki power x is equal to e to the power y, and then this you clearly easily you show that x is equal to y, is exponential of e ki power x is the same as x of y, then we can say that. So, show phi is a 1-1, we can phi of x y is equal to same for all x is equal to y, and then this is clearly e ki power x y is equal to, simply we can say that is equal to we have a, and then if you take r log of r denote the natural logarithm of r, then x can be written in the form of a just a log of e to power x. So, for e ki power y is equal to x. So, phi is 1-to-1, that is a this is on phi of log on a is equal to, you have a this, because these two are the same, and then you can say x is equal to y. So, this is phi is 1-to-1. So, we simply say that a is the element of R positive, and then for this a is greater than 0. So, phi of ln a is e to the power ln a is equal to a, that means we find an element a to the power a which is equal to a. So, a is the element of a R. So, this means clearly we can say that this phi is onto, and this implies that R positive and R under addition and R positive under multiplication is a isomorphism. These two groups are isomorphism. Okay, now we move to the prove some properties of a isomorphism. So, first is we take say phi from G to G1 and theta from G1 to KB2 group homomorphism, where the G, G1 and K are the three groups. So, we can say that it means we have to define as a phi G to G and theta is a two group isomorphism, means we have a G is isomorphic to G1 and G1 is isomorphic to K. G, G1 and K are, we have a three groups, different groups. Now, if these two are two groups isomorphism, then we say that phi inverse of a, if you take a phi inverse of a G1 to G is an isomorphism, and the composition of these two, we can simply say that we have a G to G1 we have a phi, and we have a G1 to we have a k is equal to, we have a theta, and then there is a group, this is nothing but is equal to theta composition phi, and that group is a from G to k is, then we say that if these two are isomorphism, then the composition of these two groups is also isomorphism. So, we prove these two properties by one by one. We have to first we prove that if phi from G to G1 be a group isomorphism, then phi inverse of G1 to G is also an isomorphism. So, first we show that phi inverse is 1 to 1, and then you have to we show that phi inverse G1 is equal to phi of G, and then you have we have a given from G to G1 is isomorphism, that means this is equal to homomorphism, and this is also bijective. Bijective means you have a clearly is a 1 1 and onto condition is satisfied, this thing. So, if we have to show that, then we have to show that this is equal to, this means clearly we have to show that this G1 is equal to same as a G2. So, where G1 and G2 are the element of a G1. So, we just start, we operate the phi onto the both side, and then you have to know that the phi of phi inverse G1, this phi of inverse of G2, and then this can be written as a phi is a homomorphism. So, we just take a this is nothing but is equal to, if you take this is nothing but is equal to, we have to take a phi from G to G1 is a homomorphism, and then we have also 1 1 and on 2. So, if we have a phi is the element of some G1, then phi inverse is also the element of a G1, then phi into phi inverse is nothing but is equal to identity element of a some G1. So, this means this is the identity element of a some G1 identity function, and this is again now a identity function of a G1, and then is identity function of a G1. G1 is nothing but is equal to, you have a G1 to G2. So, we can simply say that if we have a phi inverse is clearly, if we taking into this form, then phi is if you know that is a 1 1 means if we have a phi is 1 1, so phi A and B are the element of this, then phi of A is equal to phi of B. So, phi of this is equal to phi of this, and then we can say that simply because you know that this is the phi inverse is a map from G1 to G, and this is the element of a G. So, this means that if you have a G1 is the element of a this, then phi inverse G1 is the element of a G, and also G have a G2, and then phi inverse G2 is the element of a G. This is the element of a G, this is the element of a G, and now G is a 1 1. So, if G is 1 1, and then you have a phi from G to G1 is a 1 1 and on 2. So, if you have any element of a G, phi inverse of a G1 is the same as a phi inverse of a G2, then phi of phi inverse of a G1 is equal to phi of phi inverse of a G2, and then this can be written as a form of a simply is a form of a this phi, then we can say the phi of phi inverse of a G1 is equal to phi of phi inverse of G2, then this is nothing but is equal to identity function of a G1, and this is equal to, we show into this form. So, this is clearly we can say that this is if phi 1 inverse is a 1 1, then first we show that phi inverse is clearly is a 1 1. Now, we have to show that this phi inverse is a onto. So, we have to show that clearly phi 1 inverse is onto. If G is the element of a G, then you clearly have a phi from G to G1. If G is the element of a G, then phi of G is the element of a G1, and then phi of G is the element of a G1, then phi inverse of phi of G is equal to, you have a identity of a G into G is equal to, you have a G. So, this means phi inverse is clearly is a also satisfy the condition of this second condition of onto. So, we have to show that this phi inverse is 1 1 and phi inverse is also then onto. Okay, now we have to show that this phi inverse is homomorphism. If phi inverse is homomorphism, this is we have to take any two, because phi inverse is you have a from G1 to G. So, you take a phi inverse of some G1 G2 composition, and then we have to show that this is the same as a phi inverse of G1 and composition of a phi inverse of a G2 in this form. Okay, so let us try. X and y are the elements of a G1, then x can be written as a phi of A, y can be written as a phi of B. Because we have to taking a we have a phi from G2, G1 is a homomorphism. I take a x is the element of a G, then phi of x is the element of a G1. Similarly, if y is the element of a this, then phi of y is also the element of a G. So, if x1, y1 is the element of a G, then x can be written as a phi of some A is the element of a G, as for some A and B is the element of a G. So, this means we can write in the form of a this, if x and y are the element of a G1, then we can write x can be written as a phi of A, y can be written as a phi of B, and then since phi is on to phi is also is on to, so hence if z is equal to, we have a phi inverse x y, then we can say if phi is on to, if z there exists some y into this x and y inverse is also there. So, phi of z is equal to, we can say that is equal to xy, because we have a phi of z is equal to xy, and then by this z is equal to this, then we have a phi of z is equal to, you have this xy, and then xy is equal to, you have a phi of A, phi of B, and this is another phi of xy, and then we can show that phi inverse z is equal to phi inverse xy is equal to AB, and if phi inverse xy is equal to AB, then phi inverse A is equal to, you have phi inverse x, and B is equal to, you have phi inverse y. So, this can be said phi inverse is an isomorphism. So, this means is also is a phi inverse xy is the same as a phi inverse x and phi inverse y, and then satisfy the condition of homomorphism. Then we have to show that this means clearly if phi is from G to G1 is isomorphism, then phi inverse from G1 to G is also an isomorphism. So, if phi is isomorphism, then is inverse also is an isomorphism. You know that the property of a bijective function, if f from a set A to B is bijective, then f inverse B to A is also is a bijective. So, inverse of this, thus means we simply say here also the same condition is holding here. If phi from G to G is a group homomorphism, isomorphism which is homomorphism which is bijective, then inverse is also is a homomorphism. Now, we have to try to prove the second one, for where the composition of these two function is 1 1 and on to and homomorphism. So, first we try from composition is 1 1, that is composition is 1 1 is very trivial. We can take a theta composition of a phi of x is equal to theta composition of a phi of y, and then you know that we have to taking is equal to G to G1 and G1 to k, that is equal to theta, that is equal to phi, and this is equal to, you have a theta composition phi. And now, if this thing means theta times of phi of x is equal to theta times of a phi of y. Now, if you have a x and y x and y are the this is because you have a x and y are the element of this G, x and y are the element of a G, then this is equal to phi of x and phi of y are the element of a G1, and then phi of x is the element of a G1, then theta times of a phi of x is the element of a k, and then similarly theta times phi of y is the element of a k, and then you know that theta is, you have a already is giving, you have a isomorphism from G1 to k. If theta is isomorphism from G1 to k, so we can simply say that this isomorphism from G1 to k. So, this means if theta is isomorphism, this means this implies that phi of x is equal to phi of y, and phi of x, if x is the element of a G, and then phi of x is the element of a G, and phi is also, you have a giving the isomorphism, that is automatically 1 1, then now using the phi is 1 1, so we can say that x is equal to y. So, if we have a theta composition phi x is the same as a theta composition phi y, then we have to show that by using, first we use the 1 1, because you have a theta is 1 1, and next time we use the phi is 1 1. So, in this case we can easily prove that this theta composition of a these two isomorphism, composition of a 2 1 1 function is again is a 1 1. This is a trivially is a one of the set theoretical result where we say that this is clearly. Now, similarly for a onto-ness, we can use the onto-ness of these two, and now this is clearly onto, because again I just say that you have a using this figure very clearly G1, and then we have a K, and that is you have a theta, and that is equal to you have a phi, and that is equal to composition of a theta composition phi. Now, you see clearly if K, we take a K is the element of a K, there exist some elements into G1 is the element of a G1 such that theta of G1 is equal to K, because theta is onto. Theta of G1 is equal to K, because theta is onto, then we can say that into this form. So, this means this theta of G1 is the element of a so this means this is clearly is onto this thing. Now, phi is also onto. So, if we have any element of G is the element of a G, there exists some element of a G1 is the element of a G1. So, you can say that if G1 is the element of a G1, there exists some element because G1 is the element of a G1, and there exists some element of G belongs to G. We can say that so if we have a G1 is the element of a G, then there exists some element G is the element of a G, where you can say that phi of G is equal to G1. And now we take a composition of this phi of G is equal to G1 and phi of G1 is equal to K. So, we can simply say that is a this composition function is also clearly is a as onto-ness is there. So, we prove that if we have a first we using the onto-ness of a theta, and then this is phi of G is onto. Phi of G is onto means phi is onto means there exists some G1 belongs to the G1G, where phi G is equal to G1, and then we have to using the some K belongs to the K, there exists some G1 is the element of a G into this form. So, this means we can say that for a K belongs to K, we can find a composition of this over G is equal to from G to K. This is clearly we have to find a inverse image. So, we can say that this means we simply say that this composition is an onto also. Now, finally, we have to show that this composition is also homomorphism. So, composition is homomorphism trivially. We take any two element of a x and y, and then we have to using this property theta composition phi, then using the property of a composition, we can say write as a theta times phi of xy, and now phi is we have to using here the phi is homomorphism. And then if phi is homomorphism, we can have theta times of phi x. This is I just write a one more step, and now by this we have to using this, and now we using here we have a theta of like this, we have a theta times of a phi of x, phi of y, and now because theta is also is a homomorphism, this can be written as theta times of a phi of x and theta times of a phi of y. Here uses a theta is a homomorphism, and now by the property of a composition function, this can be theta phi of x and theta phi of a y. So, ultimately we have to show that theta composition phi x y is the same as a theta composition phi x, theta composition phi y, and that means we can say that we have a composition of this theta and phi is homomorphism. So, we show that composition of a two isomorphism, if theta and phi are two bijective homomorphism, then composition is also is a bijective homomorphism. So, this means clearly if we have a two isomorphism function is there, then there two isomorphism theta and phi is a two isomorphism, then their composition is also an isomorphism. So, this is complete the proof of this result. Okay, now I think I just try to some other properties of this isomorphism. So we have these are the theorems. We can say that this let G and G1 be a group such that phi from G to G1 is isomorphism. Then the order of a G and order of a G1 are the same, and if G is generated by A, then G1 is also generated by phi A. That is, if G is a cyclic, then G1 is also cyclic. I just already proved that this result for in the case of a we have a group homomorphism. If G is a homomorphism and then G is a cyclic, then G1 is also cyclic. And then so these two proof is already, this is a trivial proof by the definition. By the definition is saying that G1 and because is the G1 and G1 is a isomorphism. Isomorphism, this means there exists a bijective function from G to G1. So if it is a bijective function of this means every element of here is the image of this. So bijectiveness means G1 is the G2 is a bijective, and is a bijective means we can simply say that number of element in this set and number of this element of this are the same. So it means clearly we say that the group of G and groups of G one are because they are these two by the isomorphism is clearly say that these two groups are identical. So by the definition of a bijectiveness, we can say that the number of element in G and number of element of a G1 are the same, and this result I just say that this is true because we have to already prove that in the case of a if you remember the just beginning of the previous lecture, we show that if G is a cyclic, then G1 is also cyclic if phi from G to G1 is only homomorphism. Here is a more we have to take isomorphism. If it is a result true for homomorphism, then this is automatically get it true for isomorphism also. So this means these two result I already proved. This is first one is very clear from the definition, and this one is clearly by the we have to already prove this result. If we take in place of isomorphism, we have a homomorphism, and I show that if phi from G to G1 is a homomorphism, then if G is a cyclic, then G1 is also cyclic. Now, now we have to try to see this two results saying that if H is a subgroup of a G of order n, and then phi H is a subgroup of G1 of order n. So if we say that H is a subgroup of order n, then phi H is a subgroup of a G1 is order n because of this thing. And then if A is the element of a G, order of A is equal to n, then order of A phi of A is also equal to n. So we try to prove this. So this one first one is isomorphism. Then by the isomorphism we can simply that by the bijectiveness. And then phi 1 is isomorphism. So this is generated by this phi of this, that is G is a cyclic, then G1 is isocyclic. So we just take suppose a generator. Now phi is G1 and G1 is a group. So phi of generator of this containing into the clearly is a G1, and then we have to show that the G1 is also containing the generator of this phi of A. Suppose G1 is the element of a G1, then there exists an element G belongs to G, phi of G is equal to G1 because since phi is onto. If it is phi is onto, then G1 can be written as a phi of G, and then you can then the G is the element of a G. So every element of a G can be written as a to the power n because G is a cyclic. For some n is belongs to the and now phi of G is written in the form of this. So this G1 can be written as a phi of G, and this can be written as a phi of a to the power n, and this is phi of a whole to the power n. And now we take this G can be written as a phi, G1 can be written as a phi of a whole to the power n, and this G1 is the element of a G1, and then we can say that G can be written G1 also written in the form of this thing. So this means we can say that this G1 is containing into the generated by phi of A, and then we have to already this is phi of A is generated by G1. By these two we can say that G1 is generated by phi of A, and this implies that G1 is cyclic. So, I just so this means generator, then we now the property of this phi x to the power k is the same phi of x to the power k. So, phi of G is equal to a to the power n a to the power k, and then we can say that if G1 is the element of a this generator, so G1 is containing into this, hence this is equal to this, then this implies that G1 is equal to, you have a G1 is equal to phi of A. Okay, now we have to next prove if G and G1 be a group such that phi from G to G1 is isomorphism. If H is a subgroup of a G of order n, then phi of H is a subgroup of G1 of order n. Suppose H is a subgroup of a G, then phi of E is equal to E1, and then E1 is the element of a phi of G1, and then clearly phi of H is not equal to empty. Now, we show that this phi of H is a subgroup. So, we take a phi of X, phi of H is the element of a phi of H. If we take a phi of X, phi Y is the element of H, then phi of X, phi of Y inverse can be written as a, because using the property of this phi of Y inverse is the same as a phi of Y ka whole inverse. So, phi of X, phi of Y inverse by using here, and then phi is we have giving the isomorphism, this means homomorphism. So, this is phi of x y, and then phi of x y inverse, then phi of x y inverse, because x you have a given H is a subgroup. So, if you take x and y are the element of a clearly G, then x y inverse is also the element of a G. So, this is the element of a, this is the element of a H clearly, and if it is the element of a H, then phi is the element of a phi of G1, and by subgroup criteria of a phi G1, the mapping phi is restricted to H is 1 1, mapping from H into onto this, and then this is restricted to 1 1 and onto mapping from H to phi of H. We have to take a restriction map from H to phi of H. So, if it is restricted from 1 1 and onto map phi to H, then the number of element of H and phi of H are the same. So, this order of H is the same as a order of a phi of H. Now, we have to prove the final result where G and G1 be a group such that phi of G1G is isomorphism. If A, then order of A to the power n, then order of phi of A is also n. This is very trivial. Order of A is equal to n, then A to the power n is equal to identity. Again, by this result, phi of A to the power n, we have to show that this is equal to phi of A to whole to the power n is equal to identity is equal to B as a identity of a this is equal to G E1. So, we can try it in the form, and then this is can be same as a phi of A to the power n, and A to the power n is equal to identity, and you know that phi of E is equal to E1, and he said that G to the power k is equal to identity if and only if n divides k, and then this is G in place of a G is a finite group of order n. If the order of a G is n, then n divides k. G to the power phi A to the power n is equal to, you have identity. Then the order of a that element should divide the this n. So, this means order of phi of A divides the n. By this result, we can say here is a, we have a G is a finite group of order n, then n divides the order of a k. So, by this result we can say that by order of a phi of A divides the n. Okay, so this theorem is in now we have just proved this. Now we prove this phi of order of A order of phi of n divides the n. Now we have to show that order of phi of A is equal to n. So, we have to, since phi of A to the power order to the power A is equal to identity, then phi of A to the power order of a phi of A is equal to E is equal to phi of E. So, A to the power order of phi of A is equal to identity, since phi is 1 to 1. So, and G to the power k is equal to again this result, then also we can say that n should this is equal to n should divide the order of a phi of A. So, order of A divides n and n divides the order of A, then we gives that order of phi of A is equal to n. So, this means we complete the proof of this theorem. So, now this complete this proof of this theorem. So now I have to stop today lecture here. We have to discuss some properties of this isomorphism groups. In the next class, we continue some more properties of this isomorphism, and then try to prove the isomorphism theorems. Okay, thank you very much.